We're going to provide a brief overview of batch reactors in this video. In a batch reactor, essentially a tank, almost always a liquid, except if on a small scale like in a laboratory reactor. Any large scale, it's essentially always a liquid that's stirred, so it's well mixed. It's a closed system, meaning we're not adding to or removing any material from the reactor. And because it's usually liquid phase, it means that in most cases it's constant density, and that certainly simplifies some of the analysis. By assuming it's well mixed, it means the concentration and the temperature are uniform throughout the reactor. In other words, there are no gradients within the reactor. And this is important in terms of how we analyze. It certainly simplifies dramatically the mass and energy balances because of this assumption, and it's usually a pretty good assumption. It's well mixed, there's no gradients, but both the concentration and the temperature change with time as reaction proceeds. So in general, concentration, of course, of reactants is decreasing. The temperature may be increasing depending on how we actually have the reactor set up. Indicated here that it's actually used very extensively on large scale. Certainly a larger number of products, not total volume, but a larger number of different products are made using batch reactor than any other type of reactor. Next aspect we want to discuss is the heat transfer in these reactors. So heat transfer is very important for most large-scale reactors, and this is because most reactions on large scale are exothermic, can release significant amounts of heat. So a typical arrangement is to have a batch reactor with a jacket. This is a cross-sectional view, of course. Has a jacket surrounding it with some sort of cooling liquid, for example, that circulates through the jacket to control the temperature of the reactants. So an important aspect is scaling up from a small reactor in the laboratory to a larger on a commercial scale, and in how we do the modeling. So if we're scaling up and it's isothermal, the temperature does not change with time, either because we have good heat transfer or because it's a reaction with a lot of solvent, very low heat of reaction. So if it's isothermal, then the scale up is really direct. The equations scale up directly, and so the results will not change with volume. We would have the exact same conversion for a certain time if it's an isothermal reactor. So concentration versus time is going to be independent of the size of the reactor. If it's an adiabatic reactor, no heat removal, no heat added, then also we can scale up, and the concentration versus time is going to be independent of the size. But in between these two extremes, the heat transfer, as we make the reactor larger, so as the volume increases, the surface area for heat transfer doesn't increase as fast. Double the height, double the diameter, make the volume go up a factor of 8. Heat transfer area doesn't go up a factor of 8. It's going to go up just as the diameter. So for example, let's look at just a simple idea. If it's a cylindrical reactor, certain height, diameter, so the volume then is proportional to height times this cross-sectional area. But the heat transfer area, so this is the heat transfer area, this is the height times the circumference, if we assume it's just around the sides. And for example, with dimensionless numbers, just say the lab, the value is 1 for the volume. If we increase diameter and the height by a factor of 10, we've increased the volume by 10 cubed. But we've only increased the area by 10 squared, so the ability to transfer heat changes dramatically, which means if we were to look at the temperature as a function of time, the temperature would go up much more in the larger scale reactor, so the scale up is not direct. Why use batch instead of a continuous system? Certainly there's a lot of advantages to continuous systems, so why use a batch reactor? Since they're used for large numbers of materials, there must be good reasons. If we're doing just small scale production, then it makes a lot of sense. Specialty chemicals, drugs, dyes, etc. If we're using a new process, so it might be untried, don't want to set up a continuous system until we know more that it works. For very high priced materials, we may not need to make very much. Also, they're quite valuable. If we have long reaction times, then it's possible to have the batch reactor running more easily for long residence times. If we have the possibility of rapid fouling, and so we need to be able to open the system to fix that, or similarly if we have the possibility of contamination that can destroy the products, sometimes in fermentation, this can be an issue. Certainly batch reactors are used a lot when we have a number of different reactions, so we can have one reactor and we can make over the year's time period, for example, 20, 30 products. Certainly examples where one product you run for a week and you make a year's supply of that product and then you use the reactor for something else. So the mass balance for a batch reactor is particularly simple if we're looking at something like A goes to B in liquid phase, as we expect for batch reactors. And let's say the reaction is proportional concentration of A squared. When we write the balance, change in the total number of moles. So total number of moles of A. That's what's changing. That's what we want to change. It changes with time based on rate of reaction per volume. So the rate of reaction is per volume. We multiply by volume. For this case of a second order reaction, minus sign is important because we're using up A, so the number of moles of A decreases with time. And note, for liquid phase, constant density, this volume can be factored outside the derivative because volume's not changing, and so it's independent volume. So this is related to what we're discussing for scale up. It's independent of volume, and so we can then measure how the concentration changes with time. In small scale, we expect the same. Large scale, if it's isothermal or if it's adiabatic. Now in the real system, we have to worry about other things that would affect this type of scale up. The mixing might not be as good on a large scale. Impurities may be different from laboratory very pure materials to industrial purities for larger scale. Heat transfer, as we mentioned, is going to be more difficult as we go to larger scale. The startup, so we add materials and we get up to reaction temperature, so the startup takes longer on a larger scale, and that of course can affect reaction products and selectivity. And then the reactor materials might matter. As we go to larger scale, small scale could even be a glass reactor, and large scale could be metal. We have to worry about reaction, catalytic properties of these reactor materials. So it's a brief description of batch reactors, why we might use them, what are the issues with scale-up.